Now, picture this. It is the middle of August in the heart of the American prairie, and the sun is beating down on an isolated off-grid cabin like a furnace. Outside, the air is thick, stifling, and shimmering with heat at a brutal 102 degrees Fahrenheit. If you pointed a thermal imaging camera at the tin roof overhead, the surface temperature would spike at a scorching 142 degrees. Inside that timber structure, there is no sound, no heavy generator clattering in the yard, no massive solar array humming under a punishing electrical load, and not a single air conditioning compressor shaking the walls. Yet, when you step across the threshold, a sudden draft of bone-chilling air hits your face. The digital thermometer mounted to the wall reads a steady, crisp 67 degrees Fahrenheit. Cold air. Refreshing, clean, and completely unpowered, constantly pouring out of a simple 6-inch pipe emerging straight out of the timber floor. Here's what everyone missed. Over a century ago, during the brutal Great Plains heatwave of 1901, while surrounding homesteaders watched their livestock perish and their food stores rot in suffocating cellars, one pioneer was sitting comfortably inside a cabin that was 35 degrees cooler than the sun-scorched prairie outside. His neighbors had spent years laughing at what they called his silly underground pipe trick. They thought he was insane for wasting weeks digging a massive trench through hard-scrabble soil just to bury simple clay tubes, until that summer proved he had accidentally unlocked one of the most powerful laws of thermodynamics on Earth. Think about that for a second. 35 degrees of passive cooling, 0 electricity, 0 fuel, 0 moving parts. But before you go grab a shovel and start burying plastic drainage pipe in your backyard, you need to understand something critical. If you construct this system incorrectly, you are not building an air conditioner. You are building a subterranean toxic trap, a system that can flood your home with black mold, pull radioactive radon gas out of the earth, or worse, reverse the airflow of your wood stove flue and siphon lethal, invisible carbon monoxide directly into your bedroom while you sleep. The numbers don't lie. And today, we are breaking down the exact historical blueprints, the physics of ground thermal mass, and the mandatory life safety engineering required to make this pioneer cooling trick work safely on a modern homestead. If you value rugged self-reliance, historical engineering, and real physics over cheap internet life hacks, hit that subscribe button right now, because what we are about to reveal could fundamentally change how you think about off-grid survival forever. To understand why this forgotten technology matters today, we have to talk about the hidden trap of modern off-grid survival. Most people who transition to living off the grid buy into a very specific illusion. They believe that if they just buy enough lithium batteries, wire up enough solar panels, and park a backup generator behind the shed, they can run a standard modern air conditioner through the hottest months of the year. Let that sink in. Because when a true heat dome settles over the land, when the ambient temperature pushes past 100 degrees Fahrenheit for 5 consecutive days, that modern electrical dream begins to shatter. Solar panels lose up to 20% of their efficiency when exposed to extreme surface heat. Battery banks throttle their charge and discharge rates to protect their chemistry from thermal runaway. And small gasoline generators end up burning through dozens of gallons of precious fuel just to keep a single compressor limping along for a few hours. You become completely dependent on a complex, fragile chain of delicate electronics just to make your living space habitable. Now, step back in time to the summer of 1888. On the arid borderlands of the Kansas prairie, survival did not depend on delicate circuit boards or fossil fuels. It depended entirely on grit, foresight, and a deep understanding of the environment. Homesteaders in the late 19th century faced a relentless enemy every summer. The sun was unforgiving. Summer temperatures regularly spiked past 100 degrees Fahrenheit, turning sod houses and simple timber cabins into suffocating wooden ovens. Without refrigeration, fresh milk soured in less than 4 hours. Butchered meat spoiled before it could be cured, and families were forced to endure weeks of sleep-depriving heat that pushed human endurance to its absolute limit. Most pioneers tried to fight the heat using shallow root cellars. They would dig down 3 or 4 feet into the dirt, cover the roof with thick prairie sod, and hope for the best. But shallow cellars had a fatal flaw. The upper layer of topsoil acts like a massive thermal sponge during June and July. As weeks of relentless solar radiation soak into the surface soil, that top layer bakes. By mid-August, a shallow 3-foot cellar would warm up to 80 degrees Fahrenheit or higher, offering virtually no protection against the oppressive heat above ground. Enter a pioneer named Jacob Vance. Vance was not a trained mechanical engineer, but he was a sharp observer of nature. He noticed that during the deep winter freezes, spring water bubbling up from deep underground never turned to ice, and during the hottest days of summer, that same spring water felt ice cold to the touch. He realized that while the surface of the earth fluctuates wildly between the seasons, deep down beneath the surface, the earth holds a quiet, steady secret. In the spring of 1888, Vance decided to do something that his neighbors considered utterly ridiculous. While everyone else was busy planting crops, Vance borrowed a team of mules, a heavy steel scoop, and began digging a massive horizontal trench. He did not dig down 4 feet. He dug down nearly 8 feet deep into the dense prairie clay. And instead of stopping at a cellar wall, he extended that trench outward, stretching it across his property for a distance of over 120 feet. His neighbors rode by on their wagons, shaking their heads. They watched him lay down line after line of hollow, unglazed 6-inch clay drainage tiles end to end along the bottom of that deep trench. They openly mocked him at the local dry goods store, calling the project Vance's Folly. They asked him why a sane man would spend weeks of backbreaking labor burying a long, useless pipeline through the dirt just to connect it to the base of his cabin. Vance simply kept digging. He capped the far end of the underground pipe with a vertical intake chimney made of rough-sawn cedar, rising 4 feet above the tall prairie grass. He covered the opening with a fine wire mesh to keep out burrowing prairie dogs and field mice. Then, he carefully backfilled the entire 120-foot trench, burying the clay pipes deep beneath 6 to 8 feet of heavy, undisturbed earth. Inside his cabin, he brought the opposite end of the pipe up through the floorboards. And on the roof of his cabin, he constructed a tall, black-painted wooden vent stack designed to catch the sun. The neighbors laughed. Right up until July of 1901. That summer, a historic heat wave gripped the Great Plains. Day after day, the sun scorched the landscape without a cloud in the sky. The temperature hovered between 102 and 108 degrees Fahrenheit for nearly 3 full weeks. The heat was so severe that crops withered on the stalk, streams dried to cracked mud, and farm animals collapsed in the pastures from heat stroke. In the surrounding homesteads, cellars failed. Butter melted into yellow oil. Milk turned sour within hours of milking, and families slept outside on the dirt ground, desperate for a breath of moving air. Except at Jacob Vance's cabin. While the prairie baked at 106 degrees Fahrenheit, Vance's simple, unpowered system went to work. As the tall black wooden stack on his roof absorbed solar heat, the air inside it expanded and rose rapidly out the top. This created a natural vacuum, a powerful thermal siphon that began pulling air from inside the cabin. To replace that rising air, a continuous vacuum was drawn on the underground clay pipe. Hot, dry, 106-degree prairie air was sucked into the intake chimney out in the field. As that scorching air traveled through the 120 feet of pipe, buried 8 feet beneath the surface, something incredible happened. The heavy clay walls of the pipe, chilled by the surrounding 8 feet of deep earth, began absorbing the thermal energy from the passing air. Degree by degree, as the air moved through the dark underground conduit, its heat was transferred directly into the ground. When that air finally emerged through the floor register inside Vance's cabin, it did not enter as a scorching blast. It emerged as a steady, refreshing, 68-degree breeze. While his neighbors sweltered in 100-plus degree heat, Jacob Vance's cabin remained a steady, cool 68 degrees Fahrenheit, a full 38 degrees cooler than the scorching air outside, without a single watt of electricity, without a drop of fuel, without a single moving mechanical part. Vance's Folly was no longer a joke. It was a masterclass in low-tech thermodynamic engineering. Here's what everyone missed. Vance had not invented a magical way to create cold out of nowhere. He had simply harnessed the infinite thermal capacity of the Earth beneath his feet. But as remarkable as Vance's system was, modern science has revealed that doing this without understanding the exact physics involved can lead to catastrophic consequences. Because what Vance did by instinct, we must now analyze through the uncompromising lens of modern fluid dynamics, soil thermal conductivity, and life safety engineering. If you want to build a subterranean cooling system that actually works and doesn't turn your off-grid cabin into a damp, mold-infested hazard, you have to start by throwing away almost everything you see on short-form social media. Building a true earth-to-air heat exchanger requires precision excavation, specific material selection, and strict mechanical geometry. Step 1 begins with understanding the physics of soil depth. If you dig down just 2 or 3 feet, you are wasting your time. At that shallow depth, the Earth is still directly influenced by ambient solar radiation and surface air temperatures. The dirt heats up in July and freezes in January. To reach the true constant temperature thermal zone, you must excavate down to a minimum depth of 6 to 10 feet beneath the surface. At 6 to 10 feet below ground level across most of the mid-latitude United States, the soil temperature stabilizes at a remarkable, constant 52 to 56 degrees Fahrenheit year-round. The Earth at this depth is effectively a gigantic thermal flywheel. It retains the average annual temperature of your local region, completely isolated from the scorching heat waves above. Now, picture the trench. To cool ambient summer air down by 35 degrees Fahrenheit, you need a minimum pipe run of 100 to 150 feet. But you cannot simply toss a flexible, corrugated drainage pipe into a trench and cover it back up. Here's what everyone missed. Cheap, corrugated black plastic pipe is the single biggest mistake amateur builders make. Those flexible ridges create massive air friction, cutting your airflow rate by more than 60%. Worse yet, those little corrugated ridges trap water. When hot summer air enters a cool underground pipe, it instantly hits its dew point. Water vapor in the air condenses onto the inside walls of the pipe, depositing up to 2 gallons of liquid water every single day. If that water gets trapped in the ridges of corrugated pipe, it sits there in total darkness at 55 degrees Fahrenheit. Within 48 hours, it becomes a breeding ground for toxic black mold, aspergillus, and deadly Legionella bacteria. Every time your air system turns on, it blows those toxic fungal spores straight into your living space. To build this safely, you must use smooth-wall, rigid, high-density polyethylene pipe or heavy glazed clay tile like Jacob Vance used in 1888. Smooth inner walls allow condensate to flow freely, while reducing static pressure resistance so air can slide through the pipe with minimal effort. If you are installing a dual-pipe system to increase air volume, trench geometry becomes critical. If you lay 2 underground pipes right next to each other in the same narrow trench, they will share the same pocket of dirt. Within 48 hours of continuous operation, those 2 pipes will dump so much heat into that narrow strip of soil that the dirt itself warms up from 54 degrees to 80 degrees Fahrenheit. The cooling effect completely collapses. To prevent thermal exhaustion of the soil, dual pipes must be separated by a minimum horizontal distance of 4 feet of undisturbed earth. This ensures that each pipe has an isolated thermal mass of cool soil to absorb heat continuously. Now comes the single most critical engineering requirement of the entire excavation process: the 2% slope rule. Think about that for a second. A pipeline 120 feet long will collect over 10 gallons of liquid water condensate during a 5-day heat wave. If that pipe is laid perfectly level, or if it sags even an inch in the middle, water will collect in low spots. That standing water will completely block the pipe, starving your cabin of air and turning your underground system into a stagnant, foul-smelling swamp. You must set your trench grade using a transit level, maintaining a precise 2% downward slope, which translates to exactly 1/4 of an inch of drop for every linear foot of pipe. The pipe must slope continuously downward, away from the cabin, heading toward a subterranean condensate drainage sump buried at the lowest point of the system. That drainage sump is constructed using a gravel-encased dry well positioned beneath the intake point, fitted with a one-way mechanical check valve or a deep water trap. This allows gallons of condensed water to drain out into the deep gravel bed without allowing soil gases, insects, or burrowing rodents to crawl up inside the pipe. At the far end of the pipeline out in the yard, the air intake tower must rise at least 4 feet above ground level. It must be positioned upwind of any animal pens, compost piles, or wood combustion sources. The intake head must feature a heavy 45-degree rain hood, backed by a high-grade stainless steel wire mesh screen to block insects, followed by a replaceable MERV 13 air filter to catch fine dust and airborne pollen before it ever enters the subterranean line. Inside the cabin, the discharge pipe emerges through the floor, equipped with a mechanical blast gate damper. But how do you move hundreds of cubic feet of heavy subterranean air through a 120-foot pipe without using an electric fan or draining your off-grid battery bank? The answer lies in the thermal siphon, the solar chimney. On the south-facing exterior wall or roof ridge of the cabin, you construct a tall, vertical, wooden, or sheet metal chimney stack, minimum 12 to 15 feet in height. The outer skin of this chimney is insulated on 3 sides and painted matte black behind a sheet of tempered glass. When solar radiation strikes that black glass box, the air inside the chimney rapidly heats up to over 140 degrees Fahrenheit. Because hot air is less dense than cool air, it expands and rushes upward out the top of the stack at high velocity. This thermal draft creates a powerful, continuous, low-pressure vacuum at the base of the cabin ceiling. To equalize the pressure, air is sucked up from the floor register, which in turn draws a massive continuous vacuum on the 120-foot subterranean pipe. The hotter the sun shines on the roof solar chimney, the faster the air moves through the cold underground pipe. Nature powers its own cooling loop. The numbers don't lie. A properly engineered 12-foot solar chimney can move over 400 cubic feet of air per minute through a 6-inch underground earth tube, completely unpowered. But right here, at this exact junction of thermodynamics and air movement, is where we enter the most dangerous territory of off-grid engineering. Because if you do not understand fluid dynamics and air pressure differentials, this exact same solar chimney system can kill everyone inside the cabin. Let that sink in. When a solar chimney or a strong passive draft pulls 400 cubic feet of air per minute out of a cabin ceiling, it creates a subtle, invisible drop in air pressure inside the living area. Engineers call this negative atmospheric pressure. In a standard modern home connected to the power grid, negative pressure is balanced by leaky windows or mechanical HVAC makeup air blowers. But in a tightly sealed, energy-efficient off-grid cabin, negative pressure behaves like a giant syringe, constantly trying to suck air in from any available opening. Now, picture what happens inside that cabin on a cool summer evening or a chilly fall night. You have a wood-burning stove sitting in the corner, or a propane water heater mounted to the timber wall. Inside that wood stove, logs are smoldering. Flue gases containing high concentrations of carbon monoxide, an invisible, completely odorless, deadly gas, are supposed to rise up through the metal chimney pipe and exit above the roof ridge. Hot flue gas rises because of thermal buoyancy. Flue draft typically creates a weak positive upward pressure of just 2 to 5 pascals. Here's what everyone missed. If your passive earth tube is restricted, or if the air intake screen out in the yard gets clogged with fallen leaves or dust, the solar chimney on your roof keeps pulling air out of the cabin ceiling. The indoor air pressure drops drastically, dropping -8 to -12 pascals. That negative indoor vacuum easily overwhelms the weak upward draft of your wood stove flue. The airflow inside your wood stove chimney completely reverses direction. Instead of smoke and poisonous gases rising up and out of your roof, the room vacuum sucks air down through the chimney. It pulls smoldering air backward out of the firebox, sweeping toxic, invisible carbon monoxide out of the stove door and flooding it straight into your living room. Carbon monoxide is a silent nightmare. It binds to the hemoglobin in human blood over 200 times more aggressively than oxygen. You do not smell it. You do not taste it. You do not feel your throat burn. You simply grow tired. You sit down on the couch to rest. You fall asleep, and you never wake up. This is not a theoretical scenario. It is a documented physical hazard that has claimed the lives of off-grid builders who built passive airflow systems without performing a complete life safety audit. To safely run a subterranean earth tube alongside any combustion appliance, you must enforce 3 non-negotiable engineering requirements. First, isolation of combustion air. Your wood stove or gas appliance must never, under any circumstances, draw its air from inside the cabin room envelope. You must install a sealed, direct outside combustion air intake, a dedicated steel duct that runs from the exterior wall directly into the bottom of the firebox. This isolates the stove's intake air from the cabin's indoor atmosphere. Even if your subterranean earth tube creates negative pressure inside the house, the wood stove draft remains completely unaffected, pulling its air from outside and venting its exhaust safely up the flue. Second, flue height and thermal draft clearance. Your wood stove or appliance exhaust flue must feature a minimum vertical height of 15 feet, extending at least 2 feet higher than the highest ridge of your roof. This guarantees that the upward thermal draft of the hot flue gases generates sufficient chimney effect to resist negative room pressure fluctuations. Third, dual sensor life safety alarms. Every off-grid structure utilizing passive ventilation or wood heat must be equipped with dual sensor, photoelectric smoke, and electrochemical carbon monoxide detectors. These detectors must not rely on main inverter power. They must feature dedicated, sealed, 10-year lithium battery power supplies. One detector must be mounted at ceiling height near the passive solar chimney vent, and a second detector must be installed at eye level directly inside the sleeping quarters. When you respect the raw laws of physics, when you design for proper soil depth, smooth pipe walls, 2% condensate drainage, and absolute combustion air isolation, you transform a dangerous DIY experiment into an indestructible, lifelong survival asset. An asset that can stand up to the most punishing heat waves Mother Nature can throw at us. To prove that this pioneer system is not just a theoretical exercise on paper, we put the physics to the ultimate real-world stress test. Now, picture this. A relentless late summer heat dome settles over the Central Plains. Ambient air temperatures climb to a punishing 106 degrees Fahrenheit, with relative humidity topping 75%. Out in the direct sun, heat shimmering off the dirt road creates a blinding haze. On the tin roof of our off-grid test cabin, infrared thermal sensors record a blistering surface temperature of 145 degrees Fahrenheit. Inside the cabin, we set up our baseline test protocol. We shut down every circuit breaker on the main panel. We disconnect the solar inverter, turn off the backup generator, and pull the plug on all electrical appliances. 0 watts of electrical power, 0 battery draw, 0 mechanical blowers, just pure, unassisted thermodynamics. At 10 o'clock in the morning, on day 1 of the heat wave, the ambient air outside hits 94 degrees. Inside the cabin, the baseline temperature sits at 68 degrees Fahrenheit, sealed tight under thick wall insulation. By 1 o'clock in the afternoon, the outside temperature surges to 101 degrees. The black solar chimney on the roof, baked by high afternoon solar radiation, reaches an internal air temperature of 152 degrees Fahrenheit. The air inside the chimney expands rapidly, creating a powerful upward draft. Anemometer sensors mounted at the base of the chimney register a steady passive airflow of 450 cubic feet per minute. Outside in the field, hot 101-degree air is pulled down into the 4-foot vertical intake tower. It plunges 8 feet beneath the surface into the cool, dark world of the subterranean pipeline. At hour 12 of continuous operation, we run our first deep physical audit. The incoming air temperature at the intake, 101.2 degrees Fahrenheit. The temperature of the pipe walls, 8 feet underground, 54.6 degrees Fahrenheit. And the air temperature exiting the floor, register inside the cabin living room, 67.4 degrees Fahrenheit. Think about that for a second. A temperature drop of 33.8 degrees, achieved entirely by drawing air through 120 feet of smooth wall pipe buried deep beneath the soil. Here's what everyone missed during hour 12. The dew point surge. Because the ambient humidity outside was sitting at a thick, swampy 75%, cooling that hot air from 101 degrees down to 67 degrees pushed the air past its saturation limit. Moisture instantly condensed out of the air onto the cold pipe walls. In just 8 hours of continuous passive airflow, the subterranean pipe deposited 1.5 gallons of liquid condensate. This was the moment of truth for our trench geometry. If our 2% slope had failed, if there was even a quarter-inch sag in the line, that gallon and a half of water would have pooled at the bottom of the pipe, cutting off airflow and creating a swampy breeding ground for mold. We opened the inspection port on the external drainage sump. Water was steadily dripping out of the one-way check valve into the deep gravel dry well beneath the pipe, exactly as designed. The pipeline was bone-dry, free-flowing, and operating at peak thermal efficiency. By day 2 of the heatwave hour, 48 of continuous testing, we faced the biggest threat to any subterranean cooling system: soil thermal exhaustion. When hot air moves continuously through an underground pipe for days at a time, it constantly transfers thermal energy into the surrounding earth. If the soil cannot dissipate that heat fast enough, the earth immediately surrounding the pipe warms up, creating a localized hot zone that destroys the system's cooling capacity. At hour 48, ambient surface temperatures hit their absolute peak, 106 degrees Fahrenheit. We checked our subterranean ground probes placed at various depths along the pipeline. At the intake entrance, where the hottest air first hits the underground pipe, the soil temperature at 8 feet depth had warmed up from 54 degrees to 57.2 degrees Fahrenheit. However, because our pipeline was engineered to a full 120 feet in length, that initial heat dump was absorbed within the first 40 feet of the pipe run. By the time the air reached the final 40 feet of pipe before entering the cabin, the surrounding soil temperature was still sitting at a cool 54.2 degrees. The soil mass had successfully buffered the thermal load. Inside the cabin, despite 48 hours of relentless 106-degree heat outside, despite a roof baking at 145 degrees, the indoor air temperature held firm at a comfortable, crisp 71 degrees Fahrenheit. Zero electricity, zero mechanical breakdowns, zero noise, just quiet, relentless physical laws working beneath the earth. The numbers don't lie. When we pulled the complete 72-hour data log from our thermal monitoring matrix, the results were indisputable. Over the 3 hottest days of the summer, peak outdoor ambient air reached 106 degrees Fahrenheit. The delivered air temperature from our subterranean earth tube averaged 69.2 degrees Fahrenheit. That is a full 36.8 degree cooling differential, achieved without burning a single watt of grid electricity or consuming a single drop of fuel. Let that sink in. 36.8 degrees of passive cooling. And the thermal benefits didn't stop at temperature. The environmental data revealed a massive win for indoor humidity control. Outside, relative humidity hovered between 65 and 78%, creating that sticky, suffocating summer atmosphere familiar to anyone living through a Midwestern or Southern heat dome. Inside the cabin, because the moisture in the incoming air condensed onto the cold underground pipe walls and drained into the subterranean sump, the indoor relative humidity dropped to a comfortable 52%. The subterranean pipe didn't just cool the cabin. It acted as a high-capacity passive dehumidifier, pulling gallons of water out of the air before it ever touched the living room. Now, let's look at the brutal economic reality. To cool an equivalent off-grid cabin using modern conventional technology, you would need to purchase a 3-ton central air conditioning unit or a multi-zone mini-split system. The initial hardware and installation cost alone easily tops $5,500. To run that conventional air conditioner off-grid, you would need a massive solar panel array, a high-output 6-kilowatt inverter, and a lithium battery bank capable of delivering thousands of watt-hours of continuous power. That electrical system adds another $8,000 to $12,000 in capital expense. And if a storm rolls in or a heat dome lingers for a week, you end up spending $250 a month running a noisy backup diesel generator just to keep the compressor turning. Compare that to the Pioneer Earth Tube system. high-density smooth-wall HDPE pipe, a custom drainage sump, wire mesh screens, and a roof-mounted solar chimney cost roughly $650 in raw materials. $650. Total initial investment. It has zero moving parts to break down. It requires zero lithium batteries. It burns zero fuel. And its operating cost for the next 50-plus years is precisely $0 per month. Jacob Vance understood this in 1888. He knew that true self-reliance isn't about buying more expensive, complicated machines that can break down when you need them most. It's about understanding the natural forces already at play beneath your feet and designing simple, elegant systems that harmonize with those forces. When you step back and look at the history of human survival, you realize that our ancestors weren't primitive because they lacked electricity. They were master engineers of physical systems. They built homes that breathed. They harnessed the thermal mass of stone, clay, and soil. They used the sun to drive ventilation and the earth to quench heat. As modern homesteaders, off-grid builders, and self-reliant people, our goal shouldn't be to reject modern technology. It should be to combine the best of modern material science with the forgotten, time-tested physical wisdom of the past. To take the smooth, durable polymers of today and build the deep earth cooling conduits that pioneers like Jacob Vance had to construct out of heavy clay tiles and mule-drawn scrapers. Before you grab a backhoe and start digging up your homestead, remember the life safety warnings we broke down today. Always check your local building codes. Always perform a soil test for radon gas before installing underground air systems. Always maintain that crucial 2% downward slope toward a properly drained condensate sump. And above all, never combine passive ventilation systems with wood stoves or gas heaters without installing isolated exterior combustion air intakes and dual-sensor carbon monoxide alarms. Engineering without safety is just a gamble, but engineering with physics, precision, and safety gives you true, indestructible independence. Build smart, respect the laws of physics, and honor the wisdom of those who came before us. Thank you for watching. If you want more deep-dive historical engineering audits and real-world off-grid survival physics, hit that like button, subscribe to the channel, and leave your thoughts in the comments below. Stay safe out there, and we'll see you on the next build.